everyone. In this video, we're starting a new chapter on alpha carbon chemistry. So on the top here, I have a figure showing a carbonyl group, specifically a ketone. And you'll notice that the carbon next to the carbonyl group is labeled with the Greek letter alpha. And then the carbon a little further away is labeled beta. So we'll talk a little bit about how this alpha carbon is reactive and can go through different reactions. We're also specifically going to talk about enols and enolates in this chapter. So down below, remember that ketones can tautomerize into enols. So the ketone and the enol here are tautomers. And I know this is from a while ago, so if you want to go back and review that, that might not be a bad idea, but we'll talk about it in this lecture too. And then just remember that ketones are favored over enols, typically. There are some exceptions. And then off to the right, I have a figure showing the resonance structures for an enolate. And you'll notice there's a negative charge on the carbon next to the carbonyl group in one of those resonance structures. So that could potentially act as a nucleophile. But again, we're going to talk about all of this in this lecture. I just kind of wanted to give you a preview of what this chapter is about. So let's start by going over those alpha carbons again. So let's say we have an aldehyde, and we have a chain of carbons coming off of that carbonyl group. So we can label those carbons next to the carbonyl group as alpha, then beta, then gamma, and then delta. So the Greek letter tells us how far away the carbon is from the carbonyl group. Now we don't label the carbonyl carbon, that just stays unlabeled in this situation. Okay, now the interesting thing here is that the alpha carbon has acidic protons. So potentially we could do some chemistry there. In particular, the pKa of an alpha proton is about 20, and let's compare that to just a typical proton on a typical carbon atom. So that would be about 40 to 50. And remember, the lower the pKa value, the more acidic something is. So if you have a proton on that alpha carbon, which is next to a carbonyl group, that's going to be more acidic. So let's say that we remove one of the alpha protons from our aldehyde. So that would leave a negative charge on the alpha carbon, and we can form a resonance structure. So we could move those electrons over, and that would move pi electrons up to oxygen. So now we would have a negatively charged oxygen, and then we'd have a double bond next to the carbonyl carbon. And remember that the stronger a conjugate base is, or the more stable a conjugate base is, the stronger the original acid. And here we can see we have resonance structures. And so that means we have a stable conjugate base, which means we have a relatively stronger acid. So again, that alpha proton is pretty acidic compared to just regular old protons on a regular carbon. All right, so let's look at some of the reactions that we could perform at the alpha position. And we'll see that we're going to form either an enol or an enolate, depending on what we react the alpha position with. So let's start by reacting the alpha protons with a strong base. So let's just look at acetone here. And again, we have two alpha carbons. So both of these carbons are one position away from the carbonyl carbon. And let's draw our alpha protons. And we'll just draw them on one of the alpha carbons. We don't have to show all the alpha protons here. And let's say we're reacting this with a very strong base. We'll talk about what that base will look like later on. So that base is going to deprotonate the alpha carbon. The shared electrons will be left behind on our ketone, and then we'll move pi electrons up to oxygen. All right, and then we're going to form, it looks like, a negative oxygen here. And then we'll have a double bond on the carbonyl carbon and one of the alpha carbons. Okay, so this is what we call an enolate. But notice that we could move electrons around again to create a resonance structure. So we could move one of the lone pairs from oxygen down, which will move our pi electrons over to carbon. So now the alpha carbon has a negative charge instead of the oxygen. But the hybrid structure here of this conjugate base will be really stable because of these resonance structures. Now, which of those resonance structures would be the major resonance structure? So remember that for resonance structures, if we're trying to decide which one is the major structure, we're looking for the more stable structure. And in this case, we have a negative charge on an oxygen on one structure, and then a negative charge on a carbon. Where would that negative charge prefer to exist? On the more electronegative atom, right? So that would be oxygen. So we can make a note that the resonance structure with the negatively charged oxygen is the major structure. So that would be the major contributor to the hybrid structure. The other structure is the minor structure. And we'll just put a little asterisk here and write that oxygen is more electronegative. Okay. Now, what if we react this same ketone with catalytic acid? Would we get an enol or an enolate? So let's draw our same ketone, and we'll also draw the alpha protons on one of our alpha carbons. And this time we're reacting our ketone with catalytic acid. So we'll just draw a generic acid here. Now, what do you think will happen first? So the oxygen is going to attack or grab onto a proton from the acid. So remember, this is the same from our ketone and aldehyde chapter, where we looked at, what are the steps if we react a ketone with an acid versus a base. So acidic conditions versus basic conditions. So here we have acidic conditions, and thinking back to our ketone and aldehyde chapter, we said that the first step in acidic conditions, the oxygen attacks or grabs onto a hydrogen from the acid. And then that's going to leave electrons behind on the rest of our acid, whatever that might be. All right, so let's see what we form here. So it looks like we're going to have a protonated oxygen, which will be positively charged. And the rest of the ketone is untouched. But I'll still draw those alpha protons, because we also formed a conjugate base of that acid. So now what do you think will happen? So that conjugate base can grab onto an alpha proton. The shared electrons between carbon and the proton will be left behind to form a pi bond, and pi electrons on the carbonyl group will go up to oxygen. All right, so now we have an alcohol group on the top there. We formed a double bond down below, and this looks like our enol. And then we also reformed our acid, which makes it catalytic. Okay, now let's look at what happens if we react the same ketone with catalytic base. So this isn't going to be a strong base, it's just going to be a fairly weaker base, which is why it will be a catalytic base. All right, so let's again start with our ketone, and I'm going to draw those alpha protons again. And let's say that we're starting with the hydroxide ion. Now I know normally we consider this a strong base, but in this case it's going to be a less strong base, and we'll talk about bases in the future, so don't worry if you're a little confused right now. All right, so what do we think the first step will be here? So that hydroxide is going to grab onto one of the alpha protons. That's going to leave electrons behind, and we'll move pi electrons up to oxygen. So now we have a negatively charged oxygen and a double bond. And then we also formed water. Okay, so what do you think will happen next? So that negatively charged oxygen probably wants to grab onto a proton. So it's actually going to grab a proton from our newly formed water molecule, and we'll leave electrons behind. And that gives us an enol. Plus, we get our base back, the original base, which is what makes it catalytic. Okay, so let's just summarize, because we talked about strong bases, and now we're talking about catalytic bases. So strong bases, we said, will form enolates. Less strong bases, so catalytic bases, will form Enols. And then we also said that catalytic acid forms enols. Okay. So let's talk about equilibrium, because remember, when we're talking about a ketone and its tautomer, the enol, the ketone is typically favored, right? So let's just draw a ketone here. And we'll also draw, let's put in hydroxide, our catalytic base. And we're going to try to figure out what the products would be, and then also what our equilibrium arrows would look like. So here, this first box is for our equilibrium arrows. And then you're also going to try to figure out what the products are for this reaction. So you can pause the video, try this on your own, and then when you're done, we'll go over it together. Okay. So we said previously that if you have a catalytic base reacting with your ketone, it's going to grab onto an alpha proton and eventually will form an enol. So in this case, our enol will look like that. And then we also reform our catalytic base. So we'll have hydroxide ions still floating around. So now, which side would be favored, the ketone or the enol? The ketone. So we'll draw our equilibrium arrows so that the ketone side is favored. And it's okay if your arrows were flipped, so if your longer arrow was on the bottom, that's okay. Just as long as you indicate that the reactants are favored. Now, we can actually check the amount of product. So we could use something like NMR, and we would find that about 99.99% of our reaction mixture, I guess, would be our ketone. So really only a very, very, very tiny percent of enol will form. And this is true for most keto-enol tautomerization. But there's always exceptions in chemistry. So what if we have a diketone? So here we have two carbonyl groups. And we have 3 alpha carbons. So if we react this with catalytic base, again, there are 3 different positions that the base could take a proton from. Which one do you think the hydroxide ion will attack? The left carbon, the middle carbon, or the right carbon? The middle carbon, right? Because then we would have 2 resonance structures, one on the left and one on the right. So we'll just draw an arrow to that middle alpha carbon. So what we would end up with is an enol, and notice that the hydrogen on our enol could form a hydrogen bond with the other oxygen. So that's going to further stabilize this molecule. And then we also reform our catalytic base. Okay, so looking at our ketone versus our enol, which one do you think would be favored? The enol. So if we were able to perform this in the lab, we would find that the ketone makes up about 10 to 30% of our mixture at the end, and then the enol makes up about 70 to 90% of our mixture. So the enol is actually more stable than the diketone due to H bonding and resonance. So those two things are further stabilizing the enol. So when we draw our equilibrium arrows, we're going to draw one arrow super long going towards the enol, and then the other arrow super short going towards the ketone. Okay. So now what we're going to talk about in our next few lecture videos is the reactivity of enols and enolates and the types of reactions that we can perform at the alpha carbon position. So let's look at an enolate. So we said that the enolate could have a negative charge on the alpha carbon or on the oxygen. So that means that we could potentially add an electrophile to the carbon or to the oxygen. Because remember, nucleophiles are electron rich, electrophiles are electron poor. All right, so if we add an electrophile to the negatively charged carbon, we end up with one product. If we add the electrophile to the oxygen, we end up with a different product. Okay. So even though oxygen is more electronegative and more likely to have a negative charge, the top reaction with the negatively charged carbon is actually more common. So in the next few lectures, we're going to specifically look at the top reaction where carbon attacks an electrophile and we end up with an electrophile adding to that carbon. So we'll also talk about the types of bases we can use to form enolates, and we'll go from there. So I will see you in the next video.